Hi. So here is section 10.3, polar equations. Now, we just looked at parametric equations, and parametric equations were a way to describe x and y through another variable so things could actually move through time. Now we're going to define a different coordinate system. So you're used to what we call the rectilinear coordinate system with an x and a y. Now, that means you do motion right and left, up and down to get to points. But that's not the only motion in which you can get to a point. Just imagine if somebody said, well, look over in this direction. So if I give a reference from the positive x-axis in a specific direction, I have you looking down this line. And now if I just specify some radius, then we have created a point. And that point is usually called an r theta point. Now, because there's more than one angle that gets to that, these points can have more than one name. So let's just observe that this point here at the moment, let's say that's 2 pi thirds and radius 3. This point could be 3 2 pi thirds. Well, at the same time, we could have gotten to this using a different angle. So what angle added to 2 pi thirds adds up to 2 pi, which is 6 pi thirds? Why, we could have used 4 pi thirds, except in a negative direction. So an alternate name for this point could be 3 minus 4 pi thirds. So now you can also imagine that we can wrap around again. So this could be 3, and if I add 2 pi to that, this could be 8 pi thirds. So this point in the polar coordinate system has many names, and this is a way to get to points in a different manner. Now, something odd happens if you specify an angle but a negative direction. So I want you to think of this 2 pi thirds being specified. Let's go back a negative 2. So here's a negative 2 radius and 2 pi thirds. So polar coordinates has some peculiar properties. There's a direction, there's a radius, but when the radiuses are negative, we go in the opposite direction. It's an interesting problem. Now, the strange thing about polar coordinates is that it's not a deep relationship between polar coordinates and rectilinear coordinates. In fact, if I just put a triangle in here, well, the angle theta, although it's here, I still have the sine of theta, and its height is r sine theta right here. So that means r equals r sine theta is a way to describe the y height. But given a theta, here's the cosine, and so that's x cosine direction. This is r cosine of theta. Now, I'm going to do a little check here. X squared plus y squared will be r squared cosine squared theta plus r squared sine squared theta. Factor out the r off, cosine squared plus sine squared. That's just 1, so r squared times 1. Well, yeah, Pythagoras' theorem says x squared plus the sum of the bases squared is the radius squared. So it makes sense. So in polar coordinates, a point xy is written also as r theta. And the relationship between them is y is equal to r sine theta and x equals r cosine theta. This allows you to go back and forth between rectilinear and polar. Now, we saw earlier that when we did parametric, sometimes you really don't want to go back and forth between rectilinear and parametric. The rectilinear might have a nice description for certain things, but the parametric can allow motion and some very strange paths to be formed. So what happens when we start writing down equations in polar? All right, well, let's begin with a very simple equation in polar. So we write r, and over here we write some function of theta. So the most simple function of theta is a constant. So what about r equals 4? Well, lo and behold, that's just a circle of radius 4. Because every point on this circle is 4 comma some theta, and since we didn't specify theta, theta is free to roam. This is what I call an extrusion in polar form. If I told you this is the xy plane, and I tell you I have the two-dimensional equation x equals 2, that is just not the point. It is an extrusion into the y direction because y is free to do anything it likes. Well, this was an extrusion into the theta direction, and so we whip around like that. Now, what's another pretty simple one? Well, how about r equals just a theta? Well, when theta is 0, you get 0. When theta is pi fourths, you get pi fourths, which is just a teeny bit less than 1. Pi halves is 1.5 something. Pi is out to 3. Lo and behold, let's see, 3 pi halves. By the time we get to 2 pi, that's 6. This thing is a spiral. This thing is a circle. Now, let's do the one with r unspecified. Let's do like theta equals 2 pi thirds again. Why, lo and behold, I just go to the angle 2 pi thirds, and I let r vary freely, and here's the equation theta equals 2 pi thirds. Now, I want to point out that in the rectilinear, if I specify x equals 2, I get one line. If I specify y equals 3, I get another line. They're at right angles to each other. So specifying the very minimal equation in rectilinear produces perpendicular function, not perpendicular function, perpendicular graphs. Well, doing the same thing here. I specified r equals 4, one variable, theta equals a constant, another variable. Lo and behold, this one and this one, oops, I wrote that in green. I should have written that in should have written that one in blue, sorry. It should have been theta equals 2 pi thirds. And I drew it blue. I want you to notice it seems pretty clear that they're also at a right angle to each other. In other words, the rectilinear system is a perpendicular axis as well as a polar as perpendicular axes. Now, polar form is especially suitable to using trigonometric functions. So let's write down, let's say r equals 3 cosine of theta. Now, before I go crazy with that and plot a bunch of points, the calculator is a super valuable tool in doing this. So first off, if you hit mode, as I showed you before, I can't see that too well. I'm going to have to get some better light here. Whoops. Don't know if you can see that, but I'm going to move down and move over to polar. And yeah, I don't know if that's really visible, but there we go. I put it in polar form. I'm going to turn on a light. Might cast some shadows, but I'm going to be able to see, I think, this maybe a little bit better there. So now that I'm in polar form, I'm going to go to y equals, and I'm going to put in 3 cosine of theta. All right, so I got that put in, and I'm going to have it graph it. And ooh, I don't quite see it all, but I see what looks like almost like a circle. I just need to adjust my window. I'm going to move the x a little bit bigger and graph it again. And sure enough, it looks like I go around the whole circle. In fact, it didn't quite go the whole way around the circle. And the reason, if you look at it, theta went from 0 to 3.1. I didn't have theta go to a full 2 pi, or I only had theta go to pi. In fact, this graph completes itself in one full loop when theta only varies between 0 and pi. Now, why is that happening? Well, first off, let's just take an angle here, like pi thirds. that point, r comma pi thirds, is 3 cosine of pi thirds comma pi thirds. But the cosine of pi thirds is square root of 3 over 2 times 3, and so this is 3 root 3 over 2. That's the length. But by the time we get to pi halves, why, lo and behold, this is 3 cosine pi halves, which is 0 pi halves. So in the pi halves direction, I only go up 0, so that by the time I've reached and gone around here, theta from 0 to pi halves, I've come to here. Now, as I'm going with angles over here, past pi halves but before pi, well, the cosine is going to take on negative values, so the r is plotting over here. And so here it plots from 0 to pi halves, and here it plots from pi halves to pi. Now, how many different functions are we going to take a look at? Well, the typical functions are the following. First off, r equals a cosine of theta is a circle, and it goes over a, so its center is a over 2, so it's traditional to write it r equals 2a cosine of theta, and that way it's a circle centered at a comma 0 of radius a, and it goes around counterclockwise. What do you think r equals 2a sine of theta is? Well, I should have written it in purple, but guess what? Here it is. It's a circle up there centered at 0a of radius a. Now, there are lots of different polar equations that we can play with. Some of them are special enough and historical enough that we've given them names. And there is a summary in the book of different names of these functions, and a couple of graphs that you can look at. There's lemma skates, and there's cardioids, and lots of different interesting ones. So one of the common ones that is fun to try to figure out what's happening first is the equation where you take a regular trig function, just add a constant to it. So like r equals 2 plus the sine of theta. And later on, you should try a number in front of here. First off, I'm going to do a little bit of analysis here and realize that this varies between plus 1 and minus 1. So the biggest r can be as 3 and the least r can be as 1. So, you know what? I already know it's not going to be in here. It'll touch it someplace when that's exactly minus 1. It'll touch it at 1. And it might go all the way out to 3, but it can't go beyond it. So this function exists inside of this donut. So let's plot a couple of points. Do you know some angles that make the sine equal to 0? Well, sure, or 1. These are nice numbers. The sine is 0. At pi halves, the sine is 1. And then at pi, the sine is back to 0. And at 3 pi halves, the sine is at minus 1. I'm going to put these in now. So r now is 2 plus the sine value. So it's 2 plus 0. 2 plus 1 is 3. 2 plus 0 is 2. 2 minus 1 is 1. And so now I'm going to plot these points. When theta equals 0, I'm going to go over to 2. Got too many colors. It makes it difficult. So there's 2. Now, I'm going to go to pi halves. That's going up, and it's reached 3. It's come all the way up to there. Now, by the time I get to pi, it's come back to 2 again, and by the time I get to 3 pi halves, it's reached 1. Now, I'm not sure what the shape is. There's some questions. I mean, I'm pretty sure it's smooth. But around here, is it going to come in flat? Or might it do something like this? Hence the term, maybe, cardioid. I think you should put it in your calculator and find out what this looks like. In fact, I think you should play with your calculator and try some of these. A plus B, either sine of theta or cosine of theta, and discover what they look like. You're going to have the tools available to it so you can play with them. Now, something weird happens because of the periodicity of sine and cosine. With the periodicity of sine and cosine, just as we saw with r equals 2 cosine of theta, or was it 3, that it actually finished a revolution in a very short amount of time. Maybe we can expand on that and get more than one thing to be created. We call these leaves or pieces of a petal. So what's really cool is an attempt to get a spirographic type figure. So let's see what this would look like. Let's try r equals 3, let's say sine of 2 theta. Now, we'll start with theta. Then we're going to look at 2 theta. Then we're going to look at the sine of 2 theta. And then we'll get r. And I'm going to use some pretty standard values. 0, pi fourths, I like pi thirds, pi halves, 2 pi thirds, and let's make it all the way to, we should have a 3 pi fourths, and then one of these is larger, and then we should be at pi. Let's see, we should know which one of these is larger, right? This is 8 twelfths, and this is 9 pi twelfths. Yeah, that one's larger than that one. Okay, so twice the angle. And now we're ready to take the sines. Now, you'll notice that in the period of just going up to pi, 2 theta's already gone up to 2 pi, so the sine of 2 theta is going to take on all possible values. So we're going to kind of see how r is reacting here. So the sine of 0 is 0, the sine of pi halves is 1, the sine of 2 pi thirds, that's a 60, the sine is the longer one, square root of 3 over 2, 0, this will be minus square root of 3 over 2, minus 1, and that went right back to sine is 0. Okay? And r is just 3 times that now. 0, 3, 3 root 3 over 2, 0, minus 3 root 3 over 2, minus 3, 0. Wow, it can vary all the way from 0 up to 3. So here we go. In the 0 direction, we're at 0. At pi fourths, we're out to 3 already. Did something like this. At pi thirds, we're at 3 root 3 over 2. Now, this is less than 1, so this is less than 3. We've come back a little bit here. And then we come back to 0 by the time we get to pi halves. In this little short thing, we took a loop. Now, when we're over at 2 pi thirds, we're at minus this amount. 3 pi fourths minus 3, and then we're back to 0. We've just done this. So what is happening is that we are creating leaves of a flower. And these are kind of tough to predict, but they're not terribly bad. And I recommend, again, that you put some of these into your calculator and discover how they work. So how fancy can we get? Well, we can do some pretty fancy things. These lobes can go around and misbehave and do some crazy things. However, in general, they're not meant to be really, really, really bad. Now, let's do some calculus. So, if we have a chain rule, let's say we have y is a function of x, and then x is a function of t. Well, then dy dx is equal to, well, x depends on t. So if you remember your chain rule, this is dy dt, sorry, dx, whoops, dy, sorry, I want to talk about dy dt. Well, since y doesn't really depend explicitly on t, it depends on x, I do dy dx, then I do dx dt. So now I can divide, this is like we did in parametric before, dy dx then will be dy dt divided by dx dt. Well, seems to me that I can do the same thing for polar and parametric as I can do for parametric equations. So let's do the same statement about polar form. So if y and x are related in the following way, but x is really r cosine of theta, and in polar r is written as some function of theta, that means x is a function of theta times another function of theta. So seems to me then that I could do the same thing with the y. If y is equal to r sine theta, and r is g of theta, then r is g of theta sine theta. It is very clear now that I can do dx d theta and dy d theta, which says by the chain rule that when we want to calculate calculus, the tangent lines, the way we're used to it. See, this is a slope of a tangent line using the other variables. So let's get a slope of a tangent line to a polar form by observing that dy d theta over dx d theta will be dy dx. And if you put the dx over there, you see the chain rule. Let's do an application of that. Let's do calculus on that circle that seemed pretty simplistic. So we're going to write down r equals 3 cosine of theta. Round it goes. And let's pick some point here. Let's do 30 degrees, pi sixths. So let's see, the cosine of 30 or 3, 30, 60, 90 is oh, that's not really a nice number. Sorry. I want to do a nicer number, so let's do that again. Let's do pi thirds. Why pi thirds? Because the cosine of pi thirds is half. This will be 3 halves. So this point right here is going to be 3 halves, comma, pi thirds. Now, it would be really nice to ask, well, what's the tangent line right here? Well, that's not so hard because the dy dx, which is the slope of the tangent line provided it's evaluated at a point x equals x naught, can be changed into polar form by writing dy d theta divided by dx d theta. And now that's what we wanted to calculate. But what is the dy d theta and dx d theta? We stated them, that we could do them, but do we ever take their derivatives? We better. So let's write this down again. R is this function of theta. Y was equal to r sine theta. So dy d theta, that's the product rule. That's going to be g prime of theta sine theta plus g of theta cosine of theta. So g prime is derivative of r, that was evaluated. Our g of theta is 3 cosine of theta, so the g prime here will be minus 3 sine theta plus g of theta will be 3 cosine of theta cosine of theta. And so now we have an expression for dy d theta. And it needs to be evaluated at this point. Well, that point is using theta equals pi thirds. So that's what we'll put in here. So we're going to get a number. Now, I don't think this number looks so bad. Sine of pi thirds, let's see. Sine of pi thirds is the square root of 3 over 2. So square root of 3 over 2, square root of 3 over 2 is 3/4. So I get minus 3 times 3/4 plus, and the cosine of square root of 3 over 2 is, and pi thirds is 1/2, 1/2, 1/2, 3/4. We get minus 2 times 3 pi fourths. We get minus 3 halves. So that's dy d theta. Well, we're by no means done. Now we got to get dx d theta. Well, if you remember, x was equal to r cosine of theta. So we have g of theta cosine of theta for its rule, r cosine of theta. And so it is g prime of theta cosine of theta plus g of theta, derivative of cosine is minus sine of theta. Now we already calculated g prime of theta. The g prime of theta was minus 3 sine theta. And the g of theta was 3 cosine of theta. Why, lo and behold. No, that's not good. Pause. Well, I'm picking up where I left off when I said it was not good. No pause was necessary. I missed that minus. A minus and minus is a minus 6 cosine of theta, sine of theta. And now we can evaluate this at pi thirds. So evaluated at pi thirds, that's the square root of 3 over 2. That's 1/2, so we get minus 6 square root of 3 over 2 times a half. So we get a value, and that value goes into the bottom. And so guess what? We've just found the slope of this tangent line. Now, is it on the right side? Is it on the left side? I probably drew it poorly, but what's fun about these now is to find these derivatives. You can either remember how to do these formulas or you can memorize them. I prefer always to rederive them, but if you look at page 663, they will give you the formula for the dy dx from the polar form. On page 665, they give you, as we did the other time, these kind of neat spirographical images. And these are, they're just kind of fun to do. And they take some pretty crazy forms. One of the ones that just boggles the mind for me is r equals sine cubed of 2.5 theta plus cosine cubed of 2.5 theta. And when you guys graph this, and once you do it on your calculator, make your t-step really, really slow so that it takes a lot of points to graph so you can see this thing being created. Because it's not going to be created in the manner that you think it's going to. Put this into your calculator and then compare it up against the figure 16 given on page 665. It's pretty much almost impossible to predict that. And numerically, we can sit down and we can work on sizes and the like. So, for example, you know that sines and cosines are bounded by 1, so this could be a minus 1, this could be a minus 1, possibly. So it's very clear that r might be as low as minus 2, and it could be up as high as 2, and that means it's going to do these weird things. It could cross the origin, come back. And when are these going to be equal? And I bet they're equal frequently, and then it'll come back to the origin on regular basis. All right. Enjoy. I will put up WebAssign for this, and then we will be talking, also getting a form about when those of you that are taking the limited test, what time I should send it out to you. And for those of you that are going to take the next test, I think it's going best if we put that on the weekend or Monday. You guys just tell me where those that need the extended time, and I'll accommodate those times.